calculus so far? We started looking at shortcut rules for what is a derivative, but the bottom line is, what is a derivative? So derivative is what we call an instantaneous rate of change function. Instantaneous, there we go, rate of change. How do you get instantaneous rate of change? Well, you take rate of change, and to make that in an instant, you take a limit. And our standard way of doing that is our derivative function, f prime of x, also known as the derivative with respect to x of f of x, is equal to the limit as h goes to 0, at least this is one of the definitions, of f of x plus h minus f of x all over h. So we've been busting our butt with this process here, and this is a process right there for weeks now, and now we're seeing patterns, so we don't have to use this definition all the time. We just say, hey, that's a polynomial. I know how to do a polynomial without applying the limit directly because I know the patterns. But I'm just going to do another example of this and then some more patterns. So we looked at the power rule the other day, the sum and difference rules. Today we're going to move on to the product and quotient. But first, some functions that don't quite fit into those categories, but there's a pattern. So the one I want to look at first is f of x equals the square root of x. Ooh, it doesn't go there. And I'm going to apply the limit definition to that. And I'm going to do it all in one shot, which kind of defies my process earlier, but that was the learning process. My hope is you've moved a little bit beyond that and you can handle this. So I put an x plus h inside the function, which is what this says to do up here. And then I subtract the original function and I divide by h. And we've learned that if we try to cheat at first shot on these, we get 0 over 0, which gives us no information. So we have to do some algebra. Typical algebra with a square root quotient like this is to multiply top and bottom by the conjugate. The conjugate of that would be almost the same expression, but with a plus in between. So again, what's the point of this? My point is, what is a derivative? This is a derivative right here. This is what it means to be a derivative. To try and find the slope at a point xy. And this is the process. And now we're observing shortcuts from patterns that we perceive. So I'm going to show a pattern here. Now, the nice thing about this becomes the difference of squares in the numerator here. And the numerator collapses delightfully. So I get the square root times itself, which is just x plus h. Put my limit in here. I get the square root times itself here, which is just an x, and they're being subtracted. So the x's subtract out there. And in the bottom, I have h times that funky square root sum, which does not reduce. Nothing cancels. However, here I have a number minus itself. So that turns to 0 plus h here. And then I have an h divided by h. H divided by h is 1, right? So the x's become a 0, and then I get a 0 plus 1 in the numerator, which is 1. And when I take the limit, now if I try to cheat and let h go to 0, this is the only h there. And so I get that this right here is 1 over the square root of x plus the square root of x, which is 1 over twice the square root of x. And this is a good one to commit to memory. So we don't have to do this top stuff again. So if I see a square root function, depending on how complicated it is, its derivative is going to look something like that. Now, I'm going to take this a step further with algebra to connect it to some work we did yesterday. Hopefully you remember that the square root function is also the power 1/2. So what I have right here could be written as 1 over 2 x to the 1/2. I could take that a step farther. I could pull the 1/2 out. And then x to the 1/2, I could rewrite it with x in the numerator as x to the negative 1/2. Okay, why is that important? Well, check this out. We learned a rule yesterday, super powerful rule called the power rule. That says if you take the derivative with respect to x of x to some power n, then the resulting derivative instantaneous rate of change should be n times x to the n minus 1. And it turns out, although I only proved this for n equals a whole number, that's exactly what I have here. So think about it for a minute. In this problem up here, my n is equal to 1/2. And so here's my n out front. And my power for x, so I bring that power down, that's my n. And my power should be n minus 1. Oops, that got a little messy there. And my n is 1/2. And if I take 1/2 and I subtract 1, that gives me negative 1/2. So I mentioned this the other day that the power rule is more powerful than it seems, no pun intended there, that it actually applies to negative powers, even though I didn't prove it. And it applies to fractional powers, which we have an example of here. Not quite a proof for any rational power. I only did it for the power 1/2, but it's evidence that we can use it for all kinds of powers. So what's the moral of the story? Moral of the story is a derivative is an instantaneous rate of change. And this is the formula for instantaneous rate of change, which is the formula for a derivative. We are developing shortcuts where we observe a pattern over and over again, and we say, hey, look, I see that it's always going to look like this, right? I don't need to do that every time. I've learned my lesson here. All right, same thing here. If I see a square root, I know the derivative is 1 over twice the square root. I don't need to do this every time. That's where we are now, developing more shortcut rules.